I'd like to start off this webinar by asking you a very simple question. What would you do with an extra 5 minutes? Maybe hit the snooze button to catch a few extra Z's, grab a cup of Joe or some other beverage, or maybe scroll through some social media or play a game on your phone. Now let me ask you the same question in a slightly different way. What if you could get an extra 5 minutes every time you ran a separation? Well, clearly it would make you a lot more productive. You get a lot more done by the end of the day. But it also could get you home a little bit earlier and let you do the things you really want to do, things that are important to you in your life. So there's a lot of challenges to method development, and we always kind of demonstrate it using an equilateral triangle showing that there's a proportional balance between time, money, and the quality of your run. But the truth is that there's really a limit of time and money. And so a lot of times you have to sacrifice quality to make sure that you get things done in time and in budget. What we really like to do is flatten that triangle out so you maximize the amount of quality for a minimal amount of time and money. And that difference is time back to you that can be used for other things. Okay, so we're going to do a little pop quiz here. Which would you choose? I'm showing you two different chromatograms. It's the same sample, cortisone acetate. Take a look at the resolution. Is there really any difference? How about the retention time? Well, if we look at the retention time of A versus B, B is 2.5 times faster than A. Was that because of the column? Maybe it's a different column or a high-speed column. No, exactly the same size column, same stationary phase. So what's the difference? So let's have a little fun now. Let's take the same example that we saw in the previous slide and add in a high-speed column. So this could be a little shorter, smaller particle size, whatever, and see if we can optimize it. In this case, we've now got it down to less than a minute. That saves you 7 minutes per run. So we've talked about optimizing the quality of the run and optimizing the time of the run, but we haven't talked about the effect it has on the actual cost of the run. So if we look at the first example, we've now reduced the amount of money it takes to run that sample by 14 times. In the fully optimized, we've now reduced that by 38 times. So it has a significant impact on the cost of the runs overall. So what is the difference? The difference is that the second runs were done in SFC, supercritical fluid chromatography. Let's take a real quick look at SFC, how it is similar and different from LC. On the similar side, it's still chromatography. So the equipment is very similar. We're just using CO2 liquefied as our mobile phase. It's still using the same columns, the same detectors. Your thought process, your workflow is just the same. Where it is different is that CO2 has a higher diffusion coefficient and lower viscosity. This allows you to run faster. SFC is also orthogonal to reverse phase liquid chromatography. In other words, it's not dictated by hydrophobicity. So if you look at the chart, or the graph, I should say, on the right-hand side, where the gray dots represent log P of different samples versus retention time, you'll notice that it's fairly linear, whereas the same samples in SFC are all over the place. This means that small changes in SFC can have significant impact on resolution. Let's take a quick look at resolution. And I promise this is the only mathematical equation I'm going to show in this webinar. But if we look at resolution, it's made up of 3 equal parts: efficiency, selectivity, and retention. Each of those components can be affected by modifying different aspects of our run. So in this chart, we show how modifications of things like flow rate, temperature, and percent modifier affect retention, selectivity, and efficiency, and thus resolution. Typically for reverse phase and other liquid chromatography, you only have 3 of these parameters, but in SFC you have a 4th parameter, which is pressure. And as you'll note, pressure is very important when it comes to retention and selectivity. So let's take a look at some of these modifications and how they affect resolution. In this case, triacetyl glycerides that were done in our lab. Most people are familiar with effects of temperature on the chromatography and, of course, modifier concentration. But on this last column, back pressure, if we hold everything else constant, look at the amount of change in resolution that we can affect just by changing the back pressure. This is something that's very unique to SFC. Let's switch gears just a little bit. Faster analysis doesn't happen without best-in-class instrumentation. And so I want to talk briefly about some of our instrumentation. Only Shimadzu offers a complete line of SFC solutions. In analytical systems, we have standard single-column systems, multi-column screening systems, switchable systems that allow you to run SFC and or LC. We also have preparative systems that do stacked injection or multi-fraction collection. So Shimadzu offers an LC and SFC switching system. This allows you to run both phases, SFC and LC, on the same unit. You'll also notice that we have these LPGE valves that allow you to custom blend your mobile phases, again giving you more options and opportunities to find resolution on the same system. We can take this even a step further by adding additional LPGE valves on here. Again, the more modifiers that we can add into the system gives us more combinations for different separations and hopefully for better resolution or unusual and unique resolutions. So having these different combinations are very important, especially when we're talking about chiral molecules. So let's talk about how we can elevate chiral small molecule separations. Just a quick review of chiral molecules and why they're important. Chiral molecules have a stereocenter that allow them to become mirror images, kind of like your hands. They're virtually identical in every way, shape, and form, physical, chemical properties, and so forth, but they have very different biological effects. These biological effects, especially in drugs, are referred to as chiral pharmacology. Perfect example of that is thalidomides. Whereas the R enantiomer is a very safe and effective sedative, the S enantiomer is a teratogen and causes severe birth defects. Chiral resolution has a lot of different interactions, anywhere from hydrogen bonding, steric hindrance, pi-phi interactions, dipole moments, and they range in strength from very strong to very weak, long, short. They can be attractive, repulsive. I don't want to get too hung up on all this because we could have a whole afternoon's discussion on bonding effect to molecules. But it's really important to realize that all these interactions are going on at the same time. Add in the solvent effects and the complex molecule structures of most of today's samples. And there's really no predictive model that can help you out. Again, it's not orthogonal to hydrophobicity like we saw in that graph earlier. It's all over the place. And what that really means is find the right solution for resolution. You have to do a lot of screening. So when it comes to chiral resolution, I think this is where SFC really shines because it's the best of both worlds in that it has additional parameters that you can fine-tune. Again, we talked a little bit about fine-tuning the back pressure and the effect it has on resolution. It has lower viscosity with the CO2. So that means you can run either longer columns or you can run smaller particles for additional theoretical plates. It has very fast run times and it re-equilibrates quite rapidly. Add to that the number of chiral stationary phases that are out there, the number of modifiers, and of course our custom blending that allows you to mix and match different modifiers and different additives. Put those together, it gives you more screening options, allows you to screen faster, which should give you a greater chance of finding success. So let's take a look at a very quick example from one of our many application notes. In this case, a screen was set up with a matrix of 12 different columns and 4 different modifiers. And you notice that linalool was very easily separated out in under 3 minutes. So here's an example of what happens when you change the modifier. So this is an example that came from our friends at DyeCell. It was a proprietary sample run on the same column in ODH, same flow rate, and same percentage of modifier. We just changed the modifier from methanol to ethanol, IPA to acetonitrile. Now you notice resolution on all 4 of these are pretty reasonable. However, the retention times are quite different. And it's also worth noting too that the order of evolution can actually be reversed in some instances just by changing the content of the modifier. So here's another example where we're not looking at changing the modifier, but the composite or the composition of the modifier. So you notice starting with 50% methanol CO2, there's very little resolution, if any. Up to 65%, you're starting to see reasonable resolution, 75% fully resolved, but when you go to 85%, again, it's fully resolved, but look at the difference in retention time. So we've talked a little bit about the mobile phases, but let's take a real quick dive into column naproxen, looking at the same run parameters, so the same composition of CO2, same flow rates and same injections. However, just going from a 3 micron to a sub 2 micron, 1.6. Resolution come in quite nicely, but we've also increased or I should say decreased the runtime. So here's an example of tuning of CSPs and modifiers. We've talked a lot about just binary solvent systems where it's CO2 and one other modifier, but we haven't really shown a lot of examples where we're talking about secondary modifiers. And again, this is one of the great advantages we have with custom blending on our systems. You don't need to make up all these different solvents. You can just program it in to run on the software. So again, looking at the difference between going from methanol acetonitrile, methanol and MTBE, methanol and methylene chloride, you can see a lot of range in resolution here. So the next question is, how fast can we go? All right, this is unleashed chromatography. So let's take a look at our sample here again, Depronol. And just for reference, this is an IC column with a 5 micron particle size, 4.6 by 250. If we take a high-speed column, such as a 1.6 micron particle size, 50 millimeter, and run it at as high a pressure as we can with a higher concentration of methanol, we can actually reduce the runtime from 4 minutes to 12 seconds. That's unleashed chromatography. So we've looked at SFC for chiral separations, and hopefully you've seen some great examples of how fast and how quickly you can do this. But not everybody's working with chiral molecules all the time. Does this work well with achiral? Let's take a look. So here's a real quick physics, reverse phase versus SFC. Not only is SFC faster, but the order of elution can have a really big effect, especially if you're doing something in preparative separations. So here's another example of SFC separating out a small molecule. In this case, we're using an ELS. Yes, you can use ELSD as well as mass spec, PDA, UV detectors with SFC. So this analysis of glucosaceramide, you notice that the target molecule is coming out in less than 2 minutes, total runtime less than 4. So here's an example, again, from one of our application notes. In this case, we're looking at 3 different organic light-emitting diode materials. Now, the HPLC trace doesn't look too bad here. The 3 samples are fully resolved. The run was done in less than 7.5 minutes. However, it did have some issues. First, there was concerns that the target molecules could be sensitive to degradation on the column via interaction of the solvents or the combination of solvents and stationary phase. The runs also used a significant amount of organic solvents. So they wanted to reduce down the amount of organic solvent used. And finally, we were looking for some different alternative selectivity. In other words, could we do something that would be different that would change the order of elution? So working with SFC, we find out that we can do most of those. Okay, now again, the full runtime here is a little bit longer. However, it's not having that same interaction with the organic solvents that we saw before. It did, in fact, reverse the order of elution. And on this bar graph, you'll notice we went from using well over 40 mils per run of organic solvent to well under 10. So here's another example of using SFE with SFC and QTOF for detection. So teclisonide inhalant online analysis done very rapidly, not only using SFE to extract the samples from the matrix, but then directly inject into SFC for chromatography analysis, and then QTOF for mass spec. So up to this point, we've talked almost exclusively about small molecules, whether they're chiral or achiral, but we really haven't talked about larger molecules. And that's for a reason, because this is kind of a new area in SFC technology. So there have been some really great advances right now in enhanced fluidity, unified chromatography, and so forth. And there's a paper that was put out in Angewandte Chemie a couple of years ago by the Regalado group out of Merck, in which they looked at achiral molecules, nucleosides, both linear and cyclic peptides, proteins, and ADC, separation by SFC. And they use this using a dual gradient. And you'll notice here that as the amount of CO2 goes down, the amount of water goes up. And they got some really fabulous separations out here. I think these are some of the first examples of these, especially when you look at things like cytochrome C, bovine albumin, and human transferase. Nobody would have ever really thought that these were compounds that could be done by SFC, and they are currently being looked at. So you may have noticed from the last slide, I didn't mention oligonucleotides or peptides. Well, we have worked on those. And in fact, here's an application paper that was written up in Journal Chromatography A, looking at both ion-paired and non-ion-paired separations of different oligonucleotides and comparing the retention times in SFC versus LC. And you notice just from these 2 different chromatograms, there's a substantial difference in retention times here. We've talked about a number of ways of unleashing your chromatography, but we haven't really talked about software. And so at this point, I want to switch into the software realm and talk a little bit about Lab Solutions MD, which is an analytical quality by design software that gives you solutions for method development. Now, this could be a webinar all on its own, but for the purpose of this webinar, I'm just going to go over things very briefly. And if you have any additional questions, please reach out to us. But there's 3 phases to the MD software. The first phase is a screening phase, which you basically go in, click in your different modifiers, the different columns that you want to run. The software will automatically populate a full screening run the samples for you, and give you all the data from all the runs. All that data then can be put into the optimization phase using an optimization design box. You can then optimize your run based on, say, a mobile phase or a column, or you can do gradient program temperatures and so forth. And then the final phase, you want a robustness phase. You want to make sure that this is repeatable on many different levels so that it can be validated and qualified. So here's some data from our Lab Solutions MD. You'll notice the peak tracker keeps track of your different peaks, just in case something changes in order of evolution. From the optimization, you can actually go in using the heat map, pick out, simulate the chromatogram, and if you notice, the simulated chromatogram looks almost identical to the actual chromatogram, so it's very good correlation. And then the robustness phase, again, based on where you pick that up in the heat map, you can see where minor modifications, how they will change the chromatogram or not change it. And here's an example of an optimization to angiotensin 1 to angiotensin 2. That was done in a recent application. You notice that we were able to optimize it based on just those 2 peaks and different factors. So again, this is some of the options that you have in the software. Very, very powerful. And again, if you have any additional questions or would like to see more information on that, please let us know. So no webinar about SFC and unleashing your chromatography potential would be complete without talking about prep solutions. So let's talk a little bit about prep. So you may know that we worked with the Enabling Technologies Consortium to design the next generation of preparative SFC systems. We came up with 2 that have both stacked fraction collection options or multi-fraction collection options. One of the more unique design features of our SFC prep system is the GLS, the gas liquid separator. Most companies use a cyclonic GLS, which has issues with lower recoveries and sometimes carryover. We use what's called the Lotus stream, and the Lotus stream uses an effect called the Quanta effect that allows the CO2 to escape to the side while the liquids drip down in a very controlled manner through the central needle. This allows for higher recovery, low dead volume, and can be easily cleaned because the GLS just pops out. We've also incorporated this design into what's called the micro Lotus stream GLS. This allows for analytical prep recovery. So here's our analytical system that we showed earlier, and all we've done is incorporated in a fraction collector with that micro GLS. Now this allows you to do very small samples and collect those fractions into things such as a 96 well format without splash or cross-contamination. So we've talked about analytical systems, we've talked about preparative systems. So let's put everything together and talk about a complete workflow from start to finish, optimizing and scaling up from analytical to preparative. So in this case, we start with the analytical screening system using our screening software, put in the different parameters, populate, run, and optimize an analytic. So once we have the analytical method optimized, couple investigational preparative runs for loading, optimize the loading capacity, and then as you'll notice here in this final, isolate all 5 compounds with a 500 microliter injections, 250 milligrams of material in a single shot. So to conclude this seminar, I just want to summarize a few things about unleashing the power of SFC. SFC is very simple to use. It's robust, it's reliable. It's greener in that it can save you money. It's also environmentally far greener than any LC technique out there. SFC methods are significantly faster than traditional LCs. We've seen a number of examples where it's 50% or more faster. This applies to analytical and to prep. And of course, when you're doing preparative, you don't have to worry about dry down times. SFC can also offer unique separations. We've seen this in chiral and achiral molecules, small molecules, where not only can you get unique resolution, you can also reverse or change the order of elution. And we've also seen that large molecules, including peptides and oligonucleotides, can be separated using SFC. So when you want to unleash the power of SFC, you want to talk to the innovators, the leaders in SFC technologies, and that's Shimadzu. So please give us a call. If you need any additional information, the QR code will take you directly to our webpage, or you can type in mustscsfc.com or solutionsforpharma.com. Once again, happy holidays to all. I greatly appreciate you spending some time with us today, and I hope that I've given you some information that you can take back to your lab and apply and make your life a little bit easier. So with that, thank you and have a good day.
All right, let's thank Steve Schwartz for such an exciting presentation. Again, under the resource list, you can find information about our analytical solutions. If you've not had a chance, please fill out the survey questions on the right-hand side to provide feedback and request additional information. We also encourage you and your colleagues to attend our upcoming webinars, which encompass a wide variety of application areas. The registration link is located at the bottom of this slide. And also, for any other pharma and biopharma solutions provided by Shimadzu, you can check out our pharma and biopharma homepages at solutionsforpharma.com. Now, let's switch things over to our live Q&A session. All right, hello everyone, and welcome to today's live portion of the webinar, our Q&A session. I'm Kevin Wands, Market Manager for Pharma and Biopharma at Shimadzu Scientific Instruments. And here on the line with us was our presenter today, Steve Schwartz. Steve, how's it going?
Good. Doing well, Kevin.
Good to hear, good to hear. All right, so one of the first questions that did come in for our webinar, during our webinar today, Steve, we wanted you to go into a little bit more detail about the basically how to transfer your methods from HPLC to SFC. Do you mind delving into that a little bit more, Steve?
Sure. That's a great question, and I wish I had a very simple answer, but typically SFC, if you look at it, using CO2 as your mobile phase has approximately the same polarity as methylene chloride. So making a direct transfer from polarity in normal phase HPLC is a little bit easier with doing it from normal phase LC to SFC. Going into reverse phase compounds, it's a little bit more difficult. You may recall we had that graph earlier where we showed log P versus retention times, and the green dots were all over the place. So that really does indicate that it's not as easy and straightforward to go from a reverse phase to an SFC method. The best option there is just the screen.
All right. Is SFC way more expensive to buy compared to an HPLC?
You know, there is some initial costs that are cost a little bit more, but when you look at the cost savings over time versus SFC, CO2 is relatively cheap. It's relatively inexpensive. Disposal, it evaporates, so you don't have to worry about disposing of the solvents. And that's what we're seeing the biggest push from now within many different companies is the long-term costs of running LC, especially when you come to prep. So it is cost-effective in the end.
Fair enough, fair enough. And I guess another question that just came in, I'm blanking on it, sorry. What do you, sorry. Sorry, I'm having some technical difficulties with it. So I guess it is just adding a pump for the CO2 and the back pressure regulator. Is that correct?
Really, the biggest difference between the a standard HPLC and an SFC equipment is that you're using a CO2 pump and a back pressure regulator. Now, when you do get into preparative separations or preparative systems, it's a little more complicated in that you need to have a much larger volume of CO2 liquefied delivered to the head. In analytical, it's not a big deal. You can tap into a dip tube and a cylinder. With prep, it would take several different tanks of CO2 or a large tank, but effectively, that's the only difference.
All right. And do you see an increase in bioanalysis for SFC?
You know, that's a really great question, and there's a lot of cutting-edge work being done right now. Publications are leaning that way, and in fact, we're starting to see more in ways of oligonucleotide and peptide separations. A couple examples that I showed. I'm really intrigued by the paper that the Regalato group at Merck put out, where they've done some clearly unique biological separations. I think that's it needs to be examined further as far as its wider application. But yes, the short answer is yes. There are some applications, and it's a growing area.
All right. Now, so Steve, we're both pharma people. So one question that I have for you is, what are some other challenges in pharma and biopharma right now, and how is Shimadzu addressing said challenges with its range of SFC solutions?
That's a great question. You know, the challenges are always doing things better and faster. So obviously, SFC offers a much faster way of doing resolution or isolation separations in a high-speed area. One of the areas that I think SFC's being looked at right now is what I would say micro prep. And I know that sounds like an oxymoron, but really what it is isolating small amounts of material. I think this is very important in the areas of like oligonucleotides, peptides, even proteins. The ability to isolate a small amount of a sample, whether it comes from a biological or what have you. And we're probably, I think we're the only company out there that is doing it via SFC with our microlotus collection option.
All right, awesome. Thank you so much, Steve.
Well, thank you, Kevin.
Yeah, no problem. So it looks like we are at the end of our allocated time for the webinar. I just wanted to thank everyone for all the interesting questions that they were able to write in. And since we don't have any time for any other remaining questions, if you do have any other additional questions, we will reach out to you individually to answer. We may not be able to answer today, but we will get back to it as soon as possible. Once again, I want to thank everyone for attending and participating in today's webinar. We will send you an email with a link to view a recorded version of this presentation anytime. and we encourage you and your colleagues to attend our upcoming webinars with the registration link located at the bottom of this slide. And also for any other solutions when it comes to pharma and biopharma, you can always go to our homepages at solutionsforpharma.com. Thank you, everyone. I want to thank Steve Swartz again for presenting today, and have a great day.